So hey guys, I'm Aditya Thakur and welcome back to our series on data structures and algorithms. And today we would be continuing with asymptotic notations. So first, before going into that, we would be looking at best, worst and average case scenarios. Then we would do the notations, mathematical notations required to represent the order of growth, and in this video we would be talking about the first type of notation, which is big O notation. So let's get started. Alright, so I'll head over to Paint. Okay, so yesterday we were talking about a program that I had, and I was giving it certain inputs and it was giving me a certain outputs. So let's for example say that this was a normal searching program. So I have here a list of elements. So let me just quickly draw a list. I have a list of elements right here, and this is a program. So this is a normal searching program. Let's write search. Okay, so what happens is when I run this program, it would look into this list and try to find if the element exists or not, like really basic. So I'll give it a certain input, like I can give it a certain input to this program and it will search this list and tell me if it exists or not. Okay, so a very simple example. What happens is if I run this program and I tell it to search 23. So this 23 is our first element, so it will quickly run this program, find it on the first position, and you get 23, and it will give you the output. Now what happens if now there is another case, if I can give it 65, so it will run this program, check here, check on the third element, then check on the fourth element and find it, and it will be execute. But what happens if this list is like a really long list, and in my worst case I give it to find, like some element which is at the end of the list, like 21, let's say. So it will have to check all of these elements, like it has to compare this and all these elements it will have to compare to find 21. So this will take some time for this program to execute. Now there are like a number of solutions to this. But what do we see from this program right here? Like for any given program, there are like three cases we can say which exist. The first is that it is functioning in its best case. Means we give it a number which is at the starting of the list, so this is its best case. We give it an element which is in the middle of the list, so this is an average case, like average as in average time it takes, normal, like you either search from this side or you either search from this side, it will take average time. And worst case is when the program has to for a maximum number, it has to search for a lot of time, like it will take a lot of time to execute. So this is our worst case. Okay, so we see that there are three types of cases: best, average and worst. What happens is for comparison of algorithms, like if I were to check this program, this search program with some other search program as in you can divide arrange these elements according to their you can sort these elements, like 12 can come here, and then you can try to search, like if I have to search for like for a big number, like if I have to search for 61, so I can check the middle number if it's greater or less, so I'll directly search in this half part of the list. So there are a number of algorithms, but the point is that we always look at the worst case for comparison of algorithms. Like if in the worst possible outcome, in the worst possible situation, what will be the outcome, or how much time will the program take to execute. Okay, so we are done with this. Okay, so far we saw that we have three cases for an algorithm. There is the worst case, there is the average case, and there is the best case. And comparison of different algorithms is based on the basis of the worst case, because we know what the algorithm will do in the worst case scenario. Now in yesterday's video we saw that analysis of algorithms is based on order of growth. So we had these two programs where one was growing linearly and the other was constant. So in the worst case, the one growing linearly would go up to a very high value, so that is, you know, bad, whereas this one would stay constant for any value. So you can check out the previous video if you haven't, but we learned this. So what happens is, now this order of growth that we were looking at can be now represented in three notations, three mathematical notations, which also represent these worst, average, and best cases. Now worst case is represented by big O notation. Then there is the theta for average case, and then there is omega for the best case scenario. Okay, so in this video we would be talking about big O, which is the worst case, and we will take up these average and best case in the next video. Now moving on to big O notation. So this big O notation is the exact or the upper bound. Let's talk about the mathematical definition, and I would be explaining it. Okay, so before going to the mathematical definition, let's talk about the examples that we did yesterday. So we had a function f of n. Now we had these values 5n square, 4n, 100. So what we did yesterday was there were 2 points. So there were 2 points. Like first was we had to ignore the lower bound. So in this case 4n and 100 are constants and they are lesser than n square from the list, and there from the list I had mentioned in the previous video. So yeah, so these are lower bounds, so we'll ignore them, and we'll also ignore the constant of the value. So we got this n square. Now what was this n square? This n square was the big O notation, or the worst case of this function f of n. So in terms of big O notation, we can represent this function as O of n square. Next function f of n, for this too we would ignore the lower bound. We would ignore this 5 of, we would ignore this log n, which is lesser than this n. So we would, and the second step we would ignore the constant 5. Therefore the big O notation of this function is also O of n. Okay, so this was just to make clear that we were talking about the worst case, and we can represent the notations of this function as O of n square by removing first the lower bounds and then the constant, and of this function as O of n. Once this is done, let's move on to the definition. So we are saying, we say a function f of n is equal to this O g of n if and only if there exists a constant c and n naught such that this f of n is less than multiplied this c g of n for all n is greater than equal to this n naught. Okay, so to explain these words better, let's take for example a function f of n, which let's say 4n plus 5. Okay, so I have this function 4n plus 5. Let me just plot a graph. So I'll plot this graph. I'm sorry. Okay, so this is like my 4n plus 5. This is like 5, so my 4n plus 5 would grow something like this, a normal graph plot. Now we are saying that if this is f of n, this 4n plus 5 is our f of n, we need a c g of n such that for all values, for there exists a cg of n for all n is greater than n naught. So our n is this way, so this would be our n naught. So for all values where n is greater than this n naught, means this part of the graph, this c g of n, should be greater than or equal to, or you can say this f of n should be less than this c g of n. Okay. So how do we, find like what is this? Once we find this, it would give us the big O notation. So how we will do this is, we got let me clear up the screen first. Okay. Hope my graph is more clear. These should be straight lines, but what we have, what we know is, we'll write this condition right now. So our f of n is 4n plus 5. Alright, now this should be less than equal to cg of n. Okay, there was this direct thing we were doing yesterday. I have simply taken up this condition. So we were doing this direct thing, where we ignore this and ignore the constant. So basically, now for any value that is greater than this 4n plus 5, like what should be the c value? So in most cases, this c constant value is 1 plus the constant of the highest growing term. So highest growing term in this case would be, we will ignore the lower order terms, this constant here, and we would take the constant of this highest growing term. So our c would be 4 plus 1, so it will be 5. And you can check, verbally too, 5 multiplied by this g of n would always be greater than anything that is 4 into n, plus you can add constant to it. Okay, so this is greater than equal to that value. All right, so what do we do now is, once we have got this, we'll write it again. So 4n plus 5 is less than equal to this 5n. This 4n plus 5 is less than equal to 5n. Now I'll take this n is greater than equal to this 4n will go here, 5 minus 4, so it will give me 1n and 5 will remain here. Okay, so what is this? N is greater than 5, so this 5 is our n naught, because we know n is greater than equal to n naught, so 5 is here. Now what do we learn from this statement? For all values of n that are greater than 5, we have a cg of n value which is always either equal to, this equal to is important, either equal to or greater than this f of n. Okay, so this is our big O notation, like the worst case that is possible. We will be taking up some more examples to find the big O notation, or the worst big O notation, or the worst worst case for an algorithm. So we would like do programs and try to find their big O notation, and we would be taking up theta and omega notations in the next video. Then we will do one with the examples. And so far, if you have any queries regarding to any of this, you can drop them on my Discord server under the algorithms DSA section, where we have the algorithms, data structures, and we have hacker rank, hacker earth, geeks for geeks questions. So we would be practicing all of them. We would be doing examples, and make sure to subscribe the channel. Thank you for watching.